Why physics? If we look, so we can have various models which may have a lot of information into this basic machine learning model. So that is the idea. So here the missing ingredients, if we will incorporate some sort of a physics into it, then these machine learning models are fine. Any query? Okay. So if you inject this physics into it, then these machine learning models are called physics informed machine learning models. Fine. This is not new. So involving physics or introducing physics into this machine learning model, the idea is not new. So somebody can look for a problem proposed by Lee Demart and Talleyrand in 1986, which is called 4D VAR. So FOUR, 4-dimensional variance or variational. So this is an optimization technique which involves physics and optimizer things. And this 4D VAR model is actually a popular model to understand the oceanography, weather prediction, and various other things. So this idea is not new, but RISE group actually used this idea especially for deep neural networks, and which we are going to see it in upcoming slides. Fine. So let's look at what is a neural network and how we can process PDs. So let's take a PD with initial and bounding conditions. So this n is a linear or non-linear operator over u. U is a function of t and x. T represents here time and x represents a space. So this x can be in a d-dimensional space. So that's the reason I'm taking omega to be in RD, and we have a force term. So given this PD, we can have an initial condition like this. So the task is to solve this PD using a neural network. Fine. So the basic story is, once again, we will supply some input. The input in this case is going to be time and space t and x. So what is going to be time and space t and x? So what we will do, so we have time t, let's assume is t naught to final time t. So we can break this input t naught to t, this interval, into n number of points, and similarly we can, for this domain, we can discretize the domain, and for each point we can give each point as an input to the neural network. Design this neural network like this. So this is the input t and x. So we can have L hidden layers, and these, although the figure says they are each layer we are having the same number of neurons, but we can have different number of neurons here. Fine. Initially we can assign the random weights to these random weights and bias, and the output we are representing it as, we have this u hat. Definitely this u hat is not going to approximate this u. What we can do now, we can calculate the losses. So one of the basic property of a PD for a unique solution is it should satisfy initial and boundary condition. So this u hat is not going to satisfy initially this given conditions, initial and boundary conditions. So we can calculate the loss. So loss is going to be, let's say, the two types of loss here I am mentioning. Li is representing the loss of initial condition. LB is the loss due to boundary condition, and this lambda and lambda 1 and lambda 2 are hyperparameters. Fine. So what is L1? So this L1 is nothing but the mean error. The mean error is the value of u hat minus u naught, which is the actual value. Make it whole square and then take the average again for in the space. Fine. So this is going to be my loss of initial condition, or how much my u hat differs from the initial condition. So this information is stored in this Li. Similarly, I can have a boundary loss. Boundary loss is going to be, once again, this output minus this GT, which is the boundary data, and then we can have the mean square loss, where n2 is nothing but the number of points I considered over the boundary. Fine. So once we have this Li and Lb, we can actually compute the total loss using these hyperparameters, which are essentially nothing but the constants. And our aim is to minimize this loss. We minimize this loss using any of the optimizer which I have discussed. So once the loss is minimized, we used to get the modified parameters theta, which are nothing but these weights wi's and bias bi's. And these, through this backward propagation, we used to update these weights. And once these weights are updated, we once again move in the forward direction to compute the modified u, and this process keeps on going till the time we don't achieve our desired result. Fine. So now the question, my first question is, will after sufficient number of iterations will converge to the solution of an PDE? Any one of you can answer this question? Hello, am I connected? So can you say something about this? What do you think? If I'll actually do this way, will this output will converge to U, the U hat will converge to U? What do you think? Yes or no?
Yes, sir.
The answer is no. And can you tell me why no? Uh, so, okay, the answer is hidden. Did I ever use that PD in this neural network? The answer is no. Why? Because I only The answer is no. Why? Because I only utilized the initial data and boundary data, U naught and GT. So that means it doesn't matter if I'll modify this operator n, the output remains the same. Fine. I have not utilized anywhere in my PD. So this is a simple neural network which is not called physics informed neural network. What is physics informed neural network is, if I will introduce a loss, additional loss due to physics. Fine. And what is this loss? So once again, if you recall, the things remains exactly the same, but my loss function is now modified by introducing an additional loss, which is LPHY. So LPHY is the physics loss with an hyperparameter lambda 3. What is this physics loss? This physics loss is the average loss. So what am I supposed to do is, this U hat which I have calculated, I'm going to plug it into this PDE, and if I plug it into this PDE, I'm going to get something other than capital F, essentially. So this minus this is going to be my physics loss. Fine. And this physics loss, I am supposed to average it out over some domain, over some points which I will be talking about. So these NPHY is a number of points at which I am calculating the physics loss, and these points are called collocation points. Fine. So if I will introduce this physics loss into this total loss and proceed the same thing, the machine learning model is called physics informed neural network, or in short, PINS. Fine. I hope this is clear. Fine. So what are the essential things? So we are supposed to actually train the model. So first thing is, we need to discretize the domain, which is the initial condition, as well as, give me a minute. Yes. मैं बाद में बात करूँ. Yeah. Fine. So fine. So am I audible? Yeah. So we will discretize our domain. So domain is essentially, this is for initial condition. This is for the whole domain and the boundary data. So let's xi and xb are the set of points which we are going to have on initial condition and boundary condition. Then xphy is the number of points which basically we are going to use to talk about the physics laws, and these points are called the homologation points. Fine. So now let's try to apply this physics informed neural network over a basic problem. So we are now going to talk about a one-dimensional viscous Burger equation. I hope you might have seen or familiar with this equation. This is ut plus u times ux equals to epsilon uxx. This is a parabolic problem. When epsilon goes to 0, this becomes hyperbolic, and there are lots of consequences. But here I am going to deal with only a parabolic one. Fine. So now I'm taking a domain x from -1 to 1, and the time period is between 0 to 1. Initial condition, I'm representing it as minus of sine pi x, and the boundary condition is going to be 0 at both the ends. Fine. So this is the problem, Burger's equation, I'm supposed to solve using physics informed neural network. So my physics informed neural network consists of the same thing. I'll discretize the domain and will provide the number of points here t and xi or ti and xj's as input. I'll construct a neural network, a layer neural network, and I'll be getting an output. Initially, with respect to random weights and random bias, I'll get an output. I'll calculate my total loss, which is Li times lambda 1, lambda 2 times Lb, and L3 times Lphy, initial condition loss, boundary condition loss, and physics informed loss. This loss, so if you look at this Li loss is given something like this, Lb will look like this, and Burger's equation loss will look like this. I can explain it in more detail in upcoming slides. So the idea is using this deep neural network with respect to t and x in 0t cross omega domain. This approximate solution should satisfy the physical systems. So and hence I'll plug this u hat in the nonlinear operator minus the force function, and this should converge to 0. Fine. And then it should also satisfy the initial and boundary data. So if I'll plug this u hat, the initial data, so the initial data minus u naught should approximate goes to 0. Similarly, the boundary data, if I'll plug this hat and take this gx on the left hand side, it should also goes to 0. Fine. So for this 1D Burger's equation, so the boundary, the u hat should satisfy this equation. Fine. Once again, if you recall, this is nothing but the Burger's equation. We don't have a force term on the right hand side, and hence this is going to be my physics informed loss, and this loss should go to approximate to 0. Fine. U hat is at equal to 0, comma x minus u naught x, which was the initial condition. I'll subtract it, make it a square, and I'll take mean. So this is going to be my total loss due to initial condition. Loss due to boundary condition in this case is, once again, this is the u hat function or the over the boundary. I'll calculate it, minus gx is the boundary condition. Once again, this should go to 0, and hence making a square, dividing it by the number of points I'm considering over the boundary is going to be my boundary loss. Physics informed loss is once again going to be very easy to understand, which is going to be, in this case, the same, this differential equation where you are replacing u by u hat. Fine. So maybe one of the crucial thing, if I'll go back in this physics informed neural network, is how to calculate this physics informed loss. Fine. So if you see it carefully, in this physics informed loss, we are going to have partial derivative of u hat with respect to t and x. Fine. So now if u hat is an output of this neural network, which is once again a composition of the outputs of the previous layer, this u hat is going to be a very complex function for which calculating this partial derivatives is not going to be an easy job. Right? So in order to calculate this physics loss, one can use automatic differentiation, a methodology introduced to to approximate or to calculate derivatives if the functions are given in this compositive form. It uses chain rule and it is an exact method, and its implementation is quite easy, and majority of the toolbox in Python is having a direct tool to apply or you had to compute its derivatives. Fine. Okay, so now if you recall, we have constructed a physics informed neural network for Burger's equation. So now I'm going to talk about if we will simulate it, what we are going to get. Let us see. So what was the parameter? One of the parameter was epsilon. If you recall, it was the diffusion coefficient. We assume the diffusion coefficient as 0.01 by 2 pi, a very small value, and we constructed a 7-layer deep neural networks, and in each layer we kept the number of neurons fixed as 20, and each layer is equipped with a 10 hyperbolic activation function. Recall activation function we have talked about, so we use 10h activation function for the random points, initial points. The number of points ni and nb. So ni is the number of points on the initial time t equals to 0, and nb is the number of points on the boundary. So we take 500 points randomly on initial and boundary points, and for the physics informed laws we have used 5000 collocation points within this domain using Latin hypercube sampling. I'll talk about this collocation point and lattice hypercube sampling afterwards. Don't worry, if you're not listening, assume that we have assumed 5000 points within inside the domain at which we would like to minimize the physics loss. Fine. So the situation looks like this. This is just not an exact 5000 points. It's just a random representation. So this is my domain. We have plotted the analytical solution. So at this point, this is t equal to 0. This is the initial time. So at initial times, we have taken some points randomly. This point, this part, and this part is the boundary data, so which is already provided. Over this boundary data, we have also taken some points. So total number of points over this boundary, and this boundary is 500. Fine. And inside that domain at which we would like to minimize the physics loss, we have considered 5000 points, which are chosen a technique called Latin hypercube sampling. Fine. So let us see what is going to be the solution or which we are going to get through PIN. So this is the solution, analytical solution. So since recall we are having the initial condition is minus sine pi x and domain is from -1 to 1. So in this side, the values are going to be like this in a sine form initially, and then in this form, the lower part of the sine things. Fine. And this information moves. So PIN constructed the solution almost exactly in this case. Right? And one can very easily visualize through snapshots. So at t equal to 0, if you look at this, this was the initial condition, minus sine pi x, and the PIN has constructed the same solution. When time increases, this initial condition or the initial solution, which was smooth, starts becoming having some sort of discontinuity, or because of this epsilon becomes very small. And even if you look at in different time slots, the solution, PIN solution, agrees very well with the analytical solution. Fine. One can also calculate the errors, relative L2 error, relative L3 error, and they are coming out to be reasonably small. So this gives an idea that PINs in the concept of PINs works very well for Burger's equation, for modeling Burger's equation. Right? So I think I'll take 5 minutes break. So if you have any query or questions, you can ask. So what we have discussed in this section is, yes, please. Yeah, please ask if you have any query or question. Good morning. Yeah. See, bias. See, once again, this bias is the shifting only. Fine. See, you can. Yes, yes. You try to get it like this. If you are having a data on a line which doesn't pass through origin, so how a machine will learn and will give you that result? Fine. So you need to have some, because wi into x so will give you only something which may pass. So even a single point which passes through origin, it will give you. But if you want to shift it to some other direction, maybe upside or downside, this bias is essential. It's just a shifting, nothing else. Yes. System of why tan hyperbolic is better than sigmoid. Okay, for any case, so maybe I can go back to the scenario. I can discuss with you. So the sigmoid, if you look at, see the sigmoid, the problem of the sigmoid is, so you this is actually line between 0 and 1, and it is going to work well when your input is very close to 0, in the neighborhood of 0. Otherwise you are going to have this vanishing gradient issue. And I hope you might be understanding what is this vanishing gradient issue. You understand it? No, no, maybe I'll just try to explain you. Okay, so the idea is, so if you look at my optimization things where I was updating weights and bias, there was a term del L over del W. Fine. So if you are using this sort of activation function, that term vanishes. Fine. Maybe I can, if you want, I can show you. Give me a minute. I can go to that part. So this gradient of W. Fine. So this is the term. So if this term vanishes, essentially you are not going to get an updated weights and bias. Fine, because of this factor goes to 0. So what used to happen uh, in this activation function, the sigmoid and or tan hyperbolic, if your input or output is very very large, then this vanishing gradient problem actually persists and you are not going to get an updated one. Fine. And when it comes to sigmoid or tan hyperbolic function, if you look at this, so this tan hyperbolic function is having very sharp gradient in the neighborhood of the 0 as compared to sigmoid. Another advantage of tan hyperbolic over sigmoid is, because the mean of this tan hyperbolic function is 0, and you can actually it can take negative values as well as positive values. That means the gradients are not always restricted to move in a positive direction. They may move in a negative direction and positive direction both, because gradient values can be positive or negative. I hope I am making sense. Yes, yes. Because see, if let's say the output is or the weights are more, or you want to increase the weights or you want to decrease the weights, so this gradient should not move in only particular direction. It shouldn't be always positive. It may be positive, may be negative. So this tan hyperbolic function actually allows you to take those things, because here I have explicitly mentioned that these gradients are not restricted to move in a particular direction. Particular direction, I mean to say, for the sigmoid, they are always positive. Whereas for tan hyperbolic function, you may have a negative values also. Yeah. So this is once again a nice question. This there is no rule other than this basically approximation theorems. Fine. So for, if you would like to use an arbitrary depth, so the you have to fix the width with d plus m plus 2, where d is the features, m is the input, and you need to have two additional 2 is for input and output. Fine. Otherwise, there is no thumb rule. You can actually do some experiment and you can try. There may be some literature, but not a general one for a general problem. Only we have these two approximation theorems. Yeah. Yeah, see, once again, it totally depends upon what type of problem you are solving. And there are variety of ways, variety of modules you can actually interchangeably use this Adams and LFGSB, or for the internal part, you can use Adams, and for the final output, you can use this particular one. So once again, there is no thumb rule as far as I know. Depends upon particular problem to problem. For my problem, I have used this LFGSB completely.
Sir, if you get the error approximation, is there any condition that we should get minimum 10 power minus 4 or 10 power minus 3 or 10 power minus 5 to, submit to the Q1 journals or Q2 journals? Is there anything that condition is
No,
there in pins?
no, I'll talk about this for publishing a paper. The things will come in the next talk. So in the after 5 minutes, I'll start. What are the actually shortcomings of PIN? How people have actually tried to generalize it. One can get, and what are the challenges? Yes. Mm-hmm. 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 Yeah, I got it. So I'll try to give you an idea. Maybe for the basic, the same happens if you apply pin to advection equation. Maybe in my next presentation, I'll, because this first part was just to build the basic concept of pin, because I was not aware about the participants whether they know the basic information about pin or not. So that's the reason I made this sort of presentation. So first part is over. Hopefully in 2 to 5 minutes, I'll start my second part, and then we'll talk about.
Is there any question? I think no one having questions, so we can take a break, sir.
Maybe hardly for maybe 2 minutes break.
Yes, sure.
I just would like to have some water.
Yes, sure.
12:45. Okay. What's up? Can I, can I start?
Uh, Sir, one participant's having some doubts. You can.
We want, it may differ from problem to problem. I mean, there are large number of activation functions. Some of them I have mentioned, but this list, there are large number of activation functions. Some of them I have mentioned, but this list is very huge. Fine. You can design activation function according to your choice. So that's the reason. So I may not be habitual on knowledge for all type of activation functions. So the activation functions I'm using more are the ReLU or tan hyperbolic. So you are asking. So you are saying tan. You are asking about sigmoid and tan hyperbolic. Am I right? Yeah. So this tan hyperbolic, mathematically you can obtain it through sigmoid function using this formula. Fine. Although they are connected, but this tan hyperbolic function is having little advantage, or having a feature which is advantageous if you are looking for basically gradients which can move in both the directions. Fine. and near to zero, if you try to find out, see, look at the shape. So this is bit sharp in the neighborhood of zero as compared to this sigmoid. Fine. So here the gradients are going to be large, values are going to be large, and hence the through back propagation you can have faster convergence, but not always. But not always. Once again,
So I think no. So you can continue, sir.
okay. Thank you. So up to now, what we have seen is the basic structure of PIN, physics informed neural network, and how we can apply this physics informed neural network to solve a partial differential equation. And as an example, we took specifically choose Burger's equation. Fine. But once again, if you recall, one of the important component of PIN, which differs it from simple deep learning neural method, was physics laws, right? So now the question is how to actually look for physics laws. So physics laws is essentially you putting the output of neural network to PDE and computing the laws. But this laws should be evaluated at some point in the domain. And if you look at the previous picture, so just a minute. So we have actually taken this physics laws here, computed over large number of points. If you see once again this physics laws, we took 10 times as compared to the loss of initial and boundary data. So these points are called collocation points. So how to choose these collocation points, that I'm going to very quickly talk about. So this comes under sampling strategies. So in sampling strategies, basically we would like to find out the points in the domain at which we are going to evaluate the physics laws. Fine. So what is happening if we will not do proper sampling, then the neural networks which we are developing will not be able to understand the PD constraints explicitly, and hence we can have our wrong results or results which are not going to match with the given actual solution. Fine. So maybe I can go directly to the uh, cases. So what we can do, we can have a different strategies, sampling strategies. The first one is called grid. So this grid is very easy to understand. This is like equal spacing in space and time. So this is, I'm just assuming my domain is only one dimensional in space, and additionally we are having time. So just like this. So this is just a prototype, that's it. So you can have equal spacing in space and time, and we can call it as grid. So there's nothing random here. Another one is we can generate random points within the domain and choose these points to evaluate the physics laws, which generally we use to minimize. Right? But the problem with this randomization is there may be some part of the domain in which, like this, we are choosing large number of points, and there may be some part of the domain where we are not going to use or we are not going to choose multiple points. And hence in a problem where domain are actually crucial, and like you can assume it like this, so we can have a flow problems, flow past a body, and we can have some disturbance at some particular point. So if you are not, you are choosing this random approach to minimize the physics loss, and due to this randomization you are not choosing enough number of points near to that particular issue point, so then your solution will not be actually good, sufficiently good to converge to the actual value. So this random seems to be not working. And then other than this random one, we can have uh, algorithms where you can choose points based upon some pseudo sequence generator. Fine. There are large number of pseudo sequence generator, and based upon that you can have LHS, which is lattice hypercube sampling, Halton, Hammersley, and Sobol. So Sobol, see, you can very easily see Sobol is going. Why the name is Sobol? Because you can have a sort of structure of the points in the domain. So you can somehow see S, right? So, but what I mean to say is you are generating these points randomly through a pseudo sequence generator. Fine. And in our case, we have used this LHS, Latin hypercube sampling strategy, to find out the points, collocation points. Fine. So now, up to now, we have seen how to handle physics informed neural network for different PDEs. So now this PD, these pins are used for actually majorly two kinds of problem. One is the forward problem, and the forward problem essentially means given the differential equation and proper initial boundary conditions, we can approximate the solution. Right? Another one is the inverse problem, in which we are having some data, some information, and PD, but not, we don't know complete PD. We know only there are the structure of the PD, a prototype of PD, but parameters of the PD are unknown. So our task is to approximate the parameters of the PD, and hence this falls under the category of inverse problem. Fine. We have seen already one forward problem, which was the Burger's equation. So let us look at another forward problem, which is the heat conduction equation. So 1D heat conduction equations, ut equals to mu uxx, where mu is the coefficient of diffusion. We can take a domain from 0 to 1 and time domain 0 to 1. Initial condition as sine pi t, and initial boundary condition or zero boundary condition at 0 and 1. Fine. So once again, we can construct the same pin framework, which consists of 4 layers and 64 neurons in each case. Once again, neurons are equal in all these 4 layers. And activation function here we are taking. Fine. For collocation points, we are once again taking 5,000 collocation points using this Latin hypercube sampling. So what we can see, this is the solution to the pin, and this is the analytical solution. And this pin seems to simulate the heat equation very well, which is evident from this case. And if you look at the time snaps, so initially we have a sine pi x, so hence this is the parabolic profile, and at t equal to 0, pin solution matches with the initial condition, and for different times this diffusion occurs, and the pin solution agrees very well to the analytical solution. Right? And once again, if you compute the relative errors, they are essentially very small. So, and hence we can conclude that pin works well for heat equation as well as for Burger's equation. Now look at the inverse problem. What is the inverse problem? Let's take a Navier-Stokes equation for an incompressible fluid, and these lambda is, this is lambda 1 is the pressure, these are unknowns. So we have lambda 1, lambda 2, and P pressure, these 3 parameters which are unknown. Fine. So my task is, with the given information, can we construct these parameters through pin? Fine. And if we'll try to compute this through analytical framework, it is very, very tough. Fine. So this, once again, the RISE have actually shown the working of this pin for the inverse problem in his pioneer paper in 2019. So let's see what we can do. We can actually take the input as time, space x and y. It's a two-dimensional problem, and output as pressure and psi, where psi is the stream function for which, through which we can calculate the velocities in x and y direction, u and v. Right? And the parameters lambda 1 and lambda 2 are taken as the trainable parameters, because we would like to compute this lambda 1 and lambda 2 as well as the pressure P. Fine? And which needs to be identified by the pin through minimizing the physics and formulas. Fine. So if you look at the solution of pin versus the exact solution, so this is the exact pressure. We have plotted the pressure, and this is the predicted solution of pin given by RISE. We have not done this part. RISE has actually proved. So if you look at, so the pressure contour plot, so this looks exactly same, but only the difference is these values. Look at these values, they are completely different than these values, and the reason being because pressure in this case is defined up to an additive constant. So if you look at this equation, these equations, so if I take a pressure P, or P plus C is also a pressure, so in both the cases, basically these equations are satisfied, and that is the reason this scaling is different. Otherwise, they looks very same. So what happened while calculating the physics laws? So the correct PD was assumed as taking the value 1 1, and lambda 1 is 1 and lambda 2 is assumed to be 0.01 while calculating the physics laws. But when we try to calculate the lambda 1 and lambda 2 through physics informed neural network, then this pin approximate this 1 value as 0.99 and lambda 2 value, which was 0.01, as 0.01047, which is very reasonable. Fine. And even if we introduce some noise in the data, which is 1% of the noise, Gaussian white noise in the data, then the solution of lambda 1 was almost same, as well as the lambda 2 values are almost same as were taken in the original value to generate the laws of physics and form. So this gives an indication that pin works also very well for inverse problems. Fine. Now let's look at some shortcomings of pin. So let's talk about this one, maybe one more case, 1D reaction diffusion equation. So this is a reaction differential equation, which is ut minus nu times uxx minus rho times u into 1 minus rho equals to 0. We take the domain as 0 to 2 pi, time between 0 to 1. Given this initial and bounding condition, the reaction difference, if you apply pin, it fails for this particular choice of rho, which is 5, and the viscosity coefficient is value having 3. Fine. So if you apply pin, it will fail, and one can visualize it from here. So this is the exact solution of the given problem. And if you apply pin, definitely you can very easily visualize that pin completely fails to understand the dynamics of reaction diffusion equation and fails. Fine. Now, so in this seminal paper by Krishna Priyam, so they in 2021 they have actually provided a method, or I should say a generalization of pin to handle this sort of problem. So what they say, they provided a technique which they call sequence to sequence pin training, and the idea is instead of training the pin for the whole domain, you divide that domain into some sequences of time. So earlier the regular pin says you have this initial condition, you have this boundary condition, and over this initial and boundary condition you can take some points and you can compute the loss here, and within the domain you can take the collocation points and compute the loss and train it. But this approach fails. So what did they propose? You divide the whole domain into some time segment, and first use this initial this boundary data, this much boundary data, and this much boundary data, and you train the pin, and whatsoever pin provide a solution, you use that solution as the initial condition for the next segment. Fine. So the idea is instead of taking the whole domain at a time, you take the smaller pieces, and the solution of each piece can work as an input to the another piece. Fine. And that is the reason they called it as sequence to sequence training. And if you apply this sequence to sequence training, this is just a simple algorithm. You can see this was the exact solution, this was the usual pin solution, and if you apply sequence to sequence, you can see very well that it matches or agrees very well with the exact solution. Fine. So this is one way one can actually generalize the concept of pin, and it works for reaction diffusion equation. Fine. Now another case, if I talk about a simple 1D advection equation. So this 1D advection equation, once again, pin fails to understand its dynamics. So one can very easily visualize it from here. So if you take advection equation as ut plus beta times ux equals to 0 with the initial condition sin x and a periodic boundary. So this pin fails if beta goes beyond 30. pin works very well till beta is 30. That means for a smaller value of beta, pin works well. As soon as beta becomes large, pin fails. And one can very easily visualize from these results. So here, this is the exact results for beta equal to 30, but pin gives this sort of results, which is quite evident that this result is wrong because this is an advection equation and you have sin x as the initial condition. So this initial condition due to this periodic boundary should roam within the domain without affecting its shape, which is evident from this explicit solution or exact solution. Fine. So once again, there is an approach which we call curriculum regularization, which can actually help in pin to give a results better for beta equals to 30 or beta bigger than 30 for advection equation. And this idea is you first train the pin for smaller values and then use that solution as the basic solution for while increasing the value of beta. So you can update beta and or you can start developing pin model for smaller values of beta and then use those trainable parameter as the input parameter for while training the model for larger value of beta. So if you do that, one can actually very easily visualize that the solution, which was the exact solution for this curriculum training pin, works very well. Fine. So they both matches, whereas the regular pin fails to capture the dynamics of the system. Fine. Okay. So now we have seen some applications of pin where a pin works very well in forward problems as well as inverse problems, and we have also seen some cases where pin fails, and we have also seen some cases where you can generalize the concept of pin in a smarter way to handle the situation. So now let's try to, this is a time to compile the things and talk about the advantage of pin. The first advantage of pin is mesh free. You need not to construct the mesh. You need to choose only the collocation points using any pseudo random sampling techniques. And you can solve forward as well as inverse problem with the same algorithm. So you need not to develop separate algorithms for forward problems and inverse problems. And many times, if you have some data available, pin works well for messy problems where mathematical methods or analytical concepts sometimes struggle. You can have trackable analytical solutions gradients. That means through automatic differentiation, you are computing gradients, and which are very essential when you use or when you do sensitivity analysis. Definitely, this pin is mostly unsupervised because the majority of the points you are considering is the collocation points, which are random in nature. So, and hence this is mostly unsupervised. But now, if you look at the limitations of pins, is one of the limitation is the computational cost. And why I'm saying this computational cost is because if you are going to use this automatic differentiation for calculating the partial derivatives, maybe which in your PD, which will be your first order and second order, then in that case, this pin is going to take much more time, and hence it is computationally costly. Sometimes you can have poor convergence or no convergence at all. Another important task is, if you remember, while introducing the laws, I talked about hyperparameters, which was nothing but lambda 1 Li plus lambda 2 Lb plus lambda 3 L physics. So lambda 1, lambda 2, lambda 3, which are called hyperparameters. So we do not know how to get these hyperparameters, or in other words, how to, so it depends upon problem to problem, whether if you are looking for a problem where the boundary data is more prominent as compared to the initial data, so you will try to give more value to the hyperparameter corresponds to the boundary data, as well as the similar things can happen for other case. But there is no general methodology to get these hyperparameters. Fine. So the pin we have seen works very well for many cases, but its performance deteriorates for many other cases, which also we have seen. So generally, whenever we are having discontinuities such as shock waves, chaotic waves, or convective flows, basically we have seen the pin fails. Fine. So similarly, if you are dealing with the problems with multi-physics, multi-scale, or the problem is non-smoothness or chaotic dynamics, then the pill struggles actually. Fine. But what is the overall advantage or overall picture? We can visualize it from this figure. So in mathematics, if we don't have a data, no data, but we have a theoretical model, we do only scientific computing. Fine. Here on the right hand side, if we have the only the data but no theory, we do machine learning. But if we have some data and some theory, this physics informed machine learning performs better. Fine. So it's some sort of a bridge between scientific computing to machine learning from both sides. Now, next is data-driven pin. So the data-driven pin means, so many a times we have data from some other, so we have a PD which governs the flow, but we can perform some experiments to get some information about the flow. So in addition to the mathematical structure, we have some data with us, which can come from different sources. So now the question is, can we integrate this data from experiments to the method? The answer is yes. Through pin, we can do that part, and which we will be discussing in as an application. Fine. So up to now, we have seen the working of pin, its advantage, disadvantage. So now I'm going to use this pin for traffic flow modeling. So if any one of you is having a question, quick question, you can ask. Right.
Sir, I've just checked about.
Yeah. Yes. Oh. What type of problem? What type of problem you are solving? A P Fluid flow. It's an okay. Can we discuss at the end maybe because I do not know what type of PD you are solving. Fine. And what is the initial and bounding condition? So, can we, is it possible for you to actually write down on a piece of paper or send me a through a message? Fine, because it will be very tough because a pin is see the problem with pin is it's a general structure which works for many different cases. Fine, and which do not work for many different cases also. So it's a bit tough for me to do say something about without looking at the PD. Sorry, I cannot explicitly say. Fine. Maybe we can discuss. We can discuss. I'm working on the generalization of pin, and we try to do it in a different way. I can tell you maybe later on at the end, if the time will be having some time extra time. We can actually talk about that. Fine. Yes, yes, yes. So the meaning is reasonable noise. The pin discards. So that's not an issue with the if you have a reasonable noise. But once again, the system should be having a unique equilibrium because many times what used to happen if you are having bistable system and this noise can trigger you from one equilibrium point to another equilibrium point. So in general in PD system we have only unique equilibrium points. So that's the reason majority of the cases it works. So noise is not an issue. maybe am I making some sense? So generally, when you talks about equilibrium points, so essentially means you mean to say in steady state you have a unique solution, but there are systems which can have multiple steady states. Fine. So in that case, it depends upon what initial condition you are choosing, to whom it is going to approach. Fine. But there is a terminology called switching between equilibrium points, and in nonlinear dynamics, it is called tipping. So you can actually switch between equilibrium points through noise. So while injecting noise, you have to be within that limit, that you should not jump from one equilibrium point to another equilibrium point. Okay. Mhm. You looked up from physics point of view. Is it okay? So you try to understand in the dynamics or the physics which is happening within the domain. Fine. So I'll try to talk about in my this remaining this part where we apply pin and do many things, but it fails. Then we adopted another additional strategy. Fine, which is called data-driven pins. Maybe I'll explain it in this talk. Fine. No problem. Most welcome. So now I'll talk about the pen for traffic flow modeling. So just to start with, what is traffic flow? So I'll give you a brief idea about what is traffic flow. So traffic flow is nothing but, so this traffic flow, I'm talking about the traffic flow on roads, right? Or explicitly vehicular traffic flow. So this traffic flow essentially means the vehicles are moving, they are interacting with each other. And why should we study this? Because we would like to study this to minimize the traffic congestion or traffic jam. So if somehow we know that traffic jam is about to occur, we can modify our conditions such as traffic light times and various other measures we can take to avoid traffic jam. Fine. Okay. One another important task is whether this avoiding jam is important. So the question is the answer is yes, and the reason being because you may understand the jam may be severe, and one of the biggest jam happens to be in China in 2010 over Beijing Tibet Expressway, which is almost 24 lane highway on one side, and the the jam persists for 12 days, and it was almost 100-kilometer long jam. Now you can imagine you are stuck in a jam for 12 days and the jam is 100 kilometers long. Fine. So you can imagine the situation. Now the question is, can we understand these traffic jams? And definitely we can understand it through mathematical models, but mathematical models may be having some challenge, and hence we would like to solve it through physics informed neural network. That is the idea of this remaining part of the my talk. So let's look at the first the modeling approach. We can have microscopic, macroscopic, and mesoscopic sort of model. Microscopic essentially means you model each individual car, and hence you are going to have some system of ODs. Large, so if on a road there are 300 cars, you are going to have 300 ODs in microscopic case. Fine. We can talk about macroscopic, where we are assuming the vehicles on road as particles and fluid as continuum, and we would like to have in this case partial differential equations, hardly one or two, and mesoscopic case is in between these two. So my target is, or I will be talking about this macroscopic one, fine, where we are going to have partial differential equations, and the reason is obvious because we would like to solve it through pin. Fine. So if you look at a little bit of history of this macroscopic one, maybe I can start with this slide. So the first model came into existence by Lytle and with them along with the Richard in 1955. And what did they say? So they proposed a model which was a conservation of mass. So the idea is, if on a road, if vehicles are entering from left, leaving out from right, and there is no input and output within this domain, so the mass is going to remain conserved. Fine. So this is the continuity equation of conservation of mass. So rho is the density and u is the velocity. in space and time. I'm considering road as one dimension. Fine. Okay, so now the thing is, this equation itself, you cannot solve it. Why? Because there are two dependent variable and one equation, and hence you cannot solve it. So Greenshield in 1934 has already proposed a relationship that this velocity is a function of density in equilibrium. So if you are having this information or this function, which is u of u equilibrium of the density, you can plug this u here, and then ultimately your equation is going to be the equation in a row only, and then you can solve it. Fine. So system will become consistent, and hence you can solve it. But how to construct this ue of rho? So this equilibrium function, or we call equilibrium velocity function, this should have some basic properties, such as it should be uv and ue of rho are going to be monotonically decreasing function. Why monotonically decreasing function? So one thing is pretty clear, that if there are no vehicle on the road, you are free to run with any velocity. And if rho becomes rho jam, that means there is jam, you cannot move with the velocity, or velocity should become zero. Fine. So to following this, we can actually connect it with these two simple conditions, where q is nothing but rho into u, which is the flow, and hence you can have two situations. The flow will be zero when rho density is zero, or when density becomes maximum, flow will become zero. So it's some sort of, if you try to visualize the equation of between rho and q, it is going to be parabolic downward. Fine. So maybe if you want to see, I can show you to you here. So it is density versus flow. So all these different curves are parabolic in nature. So at this particular point, at rho equal to 0, flow is 0, and when rho is maximum, this is 0. Fine. So this is called fundamental diagram, and here I have proposed different functions given by different authors, such as Greenshield, which gives a parabolic one, and this is Del Castillo maximum sensitivity curve, and this is Kerner-Konhauser fundamental diagram curve. Fine. So there are different curves available for this equilibrium function, UE of rho. Fine. The problem with this model is completely based upon this equilibrium function, and hence for non-equilibrium situations it cannot work, and traffic being a non-equilibrium systems, this model should be discarded. So this was a drawback, and then Pine in 1971 can choose or proposed an equation instead of this equilibrium flow. It posed another equation which we called equation of motion. Fine. This is similar to conservation of momentum in fluid flow. Fine. And where you have a total acceleration, which is a part of local acceleration and convective term, and this being the relaxation term, and the last term is the anticipation term. So this relaxation term, see, you are familiar with this local acceleration and convective terms, and acceleration means then whenever the vehicle is not following the equilibrium velocity, you will try to achieve the equilibrium velocity within this relaxation time tau. Fine. And this anticipation terms handles that the vehicles also try to look at the nearby vehicles and adjust their velocity. Fine. Okay. So, but there was an issue proposed by Carlo CF Dengenu, 1995, that all the second order models are having some fundamental flaw. They are not anisotropic. That means they, it is something like vehicle behind me can horn and can force me to move faster. Fine. So there was a model came in 2002 by Ryujian and et al. And this model seems to be simplistic one, and this is having no issue as the previous models were having, and this model is called velocity gradient model. So we are going to use this velocity gradient model. Fine. And what will be our task? Our task will be to simulate this model through physics informed neural network and try to match the results in different scenarios. Fine. So first thing first, what we will do, we will try to understand what is this model all about, whether this model is stable or not. So one can perform linear stability analysis. What is this linear stability analysis? So this was the model. We can assume initial conditions to be uniform, which is here in this case we have two parameters rho and u. So we can take rho naught and u naught constant values as the steady state solution. Fine. And we can give some perturbation, and we can extend this perturbation into using Taylor series and compute the stability conditions. And if you do that, the stability condition comes out to be this. Fine. So that means if this condition is satisfied, any initial perturbation will die out, and if they are being violated, this small initial or tiny initial perturbation can lead to traffic jam. So this is this condition. Once again, what is this rho u equilibrium function? So we are using u equilibrium function, which I have shown you in the figure, different. And this initial condition actually, if you take this sort of function, which is Kerner and Konhauser or Del Castillo, any function of this shape, you are going, this inequality is going to give you two values, which is rho c1 and rho c2. These are the two critical values between which the traffic is going to be unstable. So that means if you take any rho value, density value lower than rho c1 or bigger than rho c2, the traffic is going to be stable. And in between these two values, the traffic is going to be unstable. So remember this, we are going to have two values, rho c1 and rho c2, through this linear stability analysis. Right? Okay. So what we did, we constructed a physics-informed neural network for this model, which we called traffic is TSC model, and input was once again x and t, space and time, and the output was, now instead of one output, we are having density and velocity as an output, which is we are representing as an output as rho hat and u hat, which is the output of the neural network. Fine, and definitely in order to consider the physics laws, we need to construct these sort of equations. So once you have new output of neural network, you will plug it, this neural network output, into the differential equation to construct the loss function. Fine. So let's look at some case studies. So what we did, we actually took a ring road. Fine. And in this ring road, we take a ring road of length 1 unit and time we consider in 3 units. Why we are saying 1 unit, 3 units? Because in this case, we have assumed only non-dimensional parameter. That's it. Fine. So now that's the reason we are writing it as 1 unit and 3 units. This space is discretized in 241 points, and time is discretized in 960 points, and this input is being given to the neural network. Fine. We adopted Del Castillo sensitivity curve. So this was the U equilibrium. Fine. Fine. So this initial condition. So what we did, we took an initial condition which seems to be, if you see it very carefully, this seems to be a bell-shaped curve. Fine. So that means all the vehicles are actually in the starting are together, and then we allow them to move over this ring road. Fine. So while training, what we did, we took 25% of the points from initial data of one side of the boundary. And since we are assuming a periodic boundary condition, and hence the boundary data is not known to us. So in order to utilize the boundary data, we solve the problem through finite difference, and at a particular point, we have actually assumed that point, that data as the boundary data, and we choose actually 25% of the points. If you remember the points, 241 points in space and 960 points in time. So 25% of the points we assumed as initial and boundary data coming from the finite difference. When it comes to collocation points, we assume 10,000 points, and once again the sampling was Latin hypercube sampling. Fine. In addition to this boundary initial data, since the model says it is a periodic boundary condition, we have added an extra loss term to the loss term, which is nothing but this one. So this is mean square loss, and since it is periodic, so we assume that u hat at 1, x equals to 1, should be same as u hat at x equals to 0. And if they differ, this is assumed to be a loss, and hence we are actually constructing this additional loss function. And once we put them using 10 number of layers and 20 neurons in each layer using 10h hyperbolic function, and here we assumed an output activation function as sigmoid. So our solution agrees very well with the theoretical one. And when we computed the error analysis, L2 error, L infinity error seems to be reasonable within this range. Once again, as compared to the basic pin model which was proposed for Burger's equation, so the error was something like 0.00 something. So it was up to 3 decimal. But here in our case, these errors are reasonably large, and the reason being because they are relative error. And since here, if you recall, if you look at somewhere here, the values are almost zero of these densities throughout the domain. There are many points the values are zero, and if the values are zero and pin solution gives a non-zero value, then relatively the error increases. So this larger error is because of the approximations to these zero values. Fine. Another case study was the local cluster effect. What is the local cluster effect? As if you have seen, theoretically, we have find out two range of rho 1 and rho 2, between which the flow is going to become unstable. Fine. And far from these two values, the flow is going to be stable. So in this case, we actually simulated the things with the dimensions. So the speed is assumed to be 30 meter per second. This is a free speed, that is the maximum speed. So this 30 meter per second is approximately 120 kilometer per hour. And we have assumed the maximum density as 0.2 vehicles per meter, which is approximately, that means assuming each car or each vehicle is of roughly 5 meter. Fine. And the same model when we simulate, so since this local cluster effect is parameter dependent property, so and hence we give an initial disturbance. So this initial disturbance is in particular this form. And why we have assumed this form? Because the same disturbance was assumed by Kerner and Conhauser in his 1993 paper. So we would like to match the results of pin versus the analytical results or theoretical results. So that is the reason we are keeping the shape of the disturbance intact. Fine. Okay, and we assume the road is 32.2 kilometer long, and initial perturbation was, or I should say, the amplitude of the initial perturbation was 0.01 vehicle per meter, and we run the simulation for 1800 epochs, or time t equals to 1800. Fine. So the parameters which we have chosen, if you put it in the linear stability analysis, it is going to give you the range which is 0.0312 to 0.089. And remember, the maximum density is 0.2. So if I will start my simulation from 0 to this value, the initial disturbance should die out, or from 0.084 to 0.2, it should die out. And within this range, it should amplify. Fine. So once again, when it comes to pin model, we use 25,000 points in the domain. Once again, as a collocation points using Latin hypercube sampling. And what we realize, this pin fails. If we use 10 layers, 20 neurons in each layer with 10 hyperbolic function, and a function is linear. So if you look at this, this was the numerical results. Although pin tried to capture the physics of the problem, but if you look at this height of somewhere here, it completely fails. Fine. Now, what we did, we tried to add some additional information in terms of Eulerian observation. Fine. What is the Eulerian observation? What we know that in traffic flow we can have loop detectors which are installed over poles in different locations, and they can get the information and can supply to the main server who is controlling each and everything. Fine. So see, once again, in mathematical point of view or from physics point of view, you can think it of. So here is the initial condition, here is the boundary condition. Other than this initial boundary condition, you can have pollution points, which are represented by the circular dots. And within this, we can have an additional information which we can supply. So this additional information is for each space, for roughly, say, look at this, these stars, black stars. So here in this case, for 4 different x values of 4 different positions, we have supplied additional information in different time steps. Fine. These, once you are fixing positions and supplying information for different time steps, so these are called Eulerian observations. So these observations, we have supplied additional information. And how do we get these additional observations? We got additional observations by solving the PD, system of PD, through finite difference method. Fine. Once again, keeping all the basic information intact, when we reconstruct our pin model, it agrees very well with the numerical simulation by using these 6 additional observations. Fine. So that means the pin solutions can be enhanced if they are not able to capture the given dynamics by additionally using this information. Fine. And then we run it for different values of rho naught. Once again, if you recall rho naught for different values of rho naught within this range, which we got it from linear stability analysis, we got these different patterns. And if you look at the pin reconstruction, pin was able to capture the dynamics reasonably well. I'm not saying exactly, but reasonably well. Fine. Okay, so this is once again a snapshot. So if you see it carefully, this was at t equal to 0 initial perturbation, which is very tiny. This perturbation grows because of a nonlinear region, nonlinear stable region, and pin, this red dots are able to capture this one. Somehow at some point it struggles, but yeah, this model, pin model, is able to capture the dynamics reasonably well. Fine. Okay, so we have also did this error analysis, and we conclude that yeah, adding this Eulerian observations, you can construct the pin which works reasonably well as compared to the analytical method or theoretical finite difference method. Then what we did, the last part of this talk, we actually tried to apply our approach to the real data. So this ngsim data, so this is the data available freely on this website, which is an US 101 three-way data in the United States. So we took the data from 7:50 a.m. to 8:35 a.m. over US 101 on free of Los Angeles on 15th June 2005. So this data is available. And then we recorded the density and speed and over a temporal grid. So here I can show you. So this is the density data and this is the speed data. And the reason to pick this particular data for a particular time is one can actually visualize that yeah, it is a red thing somewhere here. That means density is or speed is high, density is high somewhere here. And then you can have a free zone and then once again the dense zone and free zone. Fine. So once again we apply our pin model by taking 0, 1, 2, 3, 4 different Eulerian observations on initial and boundary data, and we took 40,000 points, pollution points, using lattice hypercube sampling. And what we realized that our model, pin model, is able to actually capture the dynamics very well. Fine. And here then we also computed this 98% confidence band. That means our results or pin results remains in 98% confidence band within the solution, actual solution, in both the cases for density as well as for speed. Fine. So the message is the pin is a generic framework which works for many differential equations, different type of differential equations, but the same approach, generic approach, cannot work to solve all type of problems. So one need to understand the physics of the problem and try to, if the basic pin fails, then try to utilize the different methodologies in order to handle the situation. So this is all about from my side. I hope I finished within time. So thank you very much. And if you have any query or questions, you can ask.
You have any question? So, sir, I think there is no question.
Okay, fine. Somebody was asking in the previous, I
Yeah,
forgot his
you
name.
can come and you can ask.
Hello.
Yes, sir.
Yes, yes, yes. So what was your question? Can you once again? Okay. Mm-hmm. Fine. Fine. Mm-hmm. Mm-hmm. Okay. Okay. See, once again, yeah, I understood your point. But if FEM is struggling, so you are dealing in 2 dimension or 3 dimension? How many dimensions you are solving? 2 dimension only. Fine. But this FEM should work. Why FEM is struggling? Either the problem may be if the pendle number is large, is there some other factor which is actually dominating the whole dynamics? Uh, so did you try for, and this pin is working for smaller pendle also? Am I right? Yeah. Okay. And so essentially, your finite element and pin both are not working for larger pin pendle number. Am I right? Yeah. So that means there is some issue with the equation. Maybe you just look at your PD system for larger pendle number. There may be some limiting case where one of the term may be creating some trouble, and because see, if both of them are actually creating trouble, that means it's not the inherent property of the pin. So pin, I can understand if finite difference or finite element is working and pin struggles, then you look for some generalization of some modification in pin. But if your FEM struggles and FEM is not giving, then there may be intrinsic issue with the system of equations. Yes, yes, yeah, yes, I understood. So essentially, okay. So pendle number is the ratio of, I think it's a, yeah, yes, fine. So large means, so velocity is large, and so I think you are moving from parabolic region to hyperbolic one. So your system equations are parabolic essentially. Am I right? And while taking this larger Prandtl number, you try to see whether you are moving towards the hyperbolic like that the convective flows are dominating. Am I right? So convective part is more dominating as compared to the diffusive part. Is it okay? Am I right or wrong? Okay, because I don't work explicitly in fluid flow. I know a little bit about this fluid flow. So the there may be an issue with the equations, not with the pin. You please check whether this within this larger Prandtl number you might be having a modified systems. You please check, or whether the same PD will work for both the cases, for smaller Prandtl number or for larger one. You please check, or the simplest part is you can actually use console type of fluid any software you might be having to run your PD for larger Prandtl number. If you are getting the solution, that means your PD is intact, and then either there's an issue with your FEM or there's an issue with your pin. So nowadays you can also actually have a pin which integrates CNN, convolutional neural networks, and integrate. Fine. So we are actually extending the pin for convolutional neural networks. So actually, I have not shown that part. So that part my students are working, and we are in almost last stage. We are extending the pin to incorporate those approaches. So we are doing some mathematical analysis, and we got some results where general pin fails. But if you do that way, it will work. So you can actually look at if convolutional neural network sort of pin based upon convolutional neural networks. Okay. Thank you for listening. If anyone else is having questions, they can ask. Sure. Thank you. Thank you. Hello. Yeah, I can hear you. Okay. Okay. Yes. 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 Definitely. Definitely. Yes. No problem. Yes. Yes. You can do that part. So we have simulated something. So the system of PDs and one system, like there is an on ramp on traffic flow. So vehicles are continuously injecting into the mainstream. So one can do that part. Yes. Yes, you are right. Yes. Yes, you are right. Sorry, I could not come actually this time because of my some issue in my family. So otherwise, I would have visited. So see, thank you for inviting me. Actually, this is my first presentation on pin. We recently started working on pin. I think from last 2 years only we started working on this pin. So I am also new and learning many things related to this area. Thank you. Thanks a lot. So can I leave now? You can disconnect. Yes. Thank you. Thanks a lot. Bye bye. Good day.